ใช้มือชี้เอาเอาอย่างนี้ใช่ไหม
ใช่ค่ะมันลื่นไปกับจอ
นี่เป็นครั้งแรกที่เขากลับข้างกันนะกลับข้างกันเด็กได้ชีพอ่ะใช่เพราะว่าตารางแกวันอังคารเนี่ยซึ่งชนกับผู้ชายแกเลยต้องสลับ เฮ้ยเอ็มน้อยมีเราใช้ขนาดนี้มากไม่เป็นไรเดี๋ยวใช้ที่นี่เอาเดี๋ยวใช้มือชี้เอาเห็นไหมเนี่ยนั่งตรงนี้ได้นะ นั่งตรงนี้ได้ Okay. Thank you very much. Good afternoon, everyone. I not very familiar face. Okay, so let me ask a little bit then. Who is in the first year for the ESC? I love you. First year, all first year. You're not your second year, maybe. Okay. And that's from my group, so I asked them to just come in and take a look. So I'm supposed to not blocking this view, right? Is this like a live online or something? Hello, the world.
It's video recording.
I know you probably spend like hours trying to do this. Is it still okay? Looks good?
Yeah.
Okay.
Still okay. Still.
All right. So I guess the background from the ESE is probably more like chemical engineering, I believe. So anyone has like chemistry background? Anyone here? Well, what's your background? Like undergraduate?
Background about chemistry.
No. I mean, in like your degree, you graduate like chemical engineering, chemistry, physics, so on.
Graduate from chemistry.
Chemistry. Okay. So if we talk about titanium, zirconium, some metal, you're familiar a little bit. What about you?
Nanotechnology.
Nanotechnology. Okay. Cool.
Petrochem.
Petrochem. Okay. So you probably have seen this. Okay. A little bit. And what about what of you? Chemical engineering. Chemical engineering. All right. What about the back?
Chemistry.
We met. You said you MSE or?
Yes. We are from MSc.
Yeah, that's right. That's why you look familiar. You look familiar. Okay. And the rest chemistry from the MSc. All right. So today, I think this class is all about. What's the name of this class again? Applied catalysis. Okay. อาจารย์เปิ้ล will be the instructor of this class, right? So I'm sure later on she'll teach about heterogeneous catalysts most of the time. So today I have a chance to explain to you about homogeneous catalysis. Okay, the difference is very simple. It's just the phase we are looking at. Is it like a same phase or different phase, right? That's the main difference. But I'm not gonna say much in terms of like which one is good, which one is bad, because each of them will have their own benefit. Okay, sometimes homogeneous is the best, sometimes heterogeneous is the best catalyst. So imagine yourself if you want to build a house, okay? Don't focus on just chisel or saw or hammer. You have to use all tools available to make a certain project. Okay, so don't be too much on one thing or another. All right, so like I said, catalysis is very simple. You have seen this, we have a reactant goes to the product. So it has to go over some barrier, right? That's the activation energy. So to go over this, it's best if you have a catalyst, so the reaction doesn't have to go over this high energy there. But the main thing I want you to focus would be the catalyst only speed up the reaction, okay? It does not change the equilibrium constant. What it means is, you can see this is the starting material, this is the product, right? You can see after you add, without catalyst, after you add catalyst, nothing changed here and nothing changed here. So the energy level will be the same, okay? Only something along the way that has been changed. Okay, so that means equilibrium constant. Equilibrium constant is at equilibrium is the concentration of product divided by reactant, right? This will be the same. So let's say at equilibrium you have 90% product. If you have the catalyst, it still be 90% product. It doesn't change to 95, 90. It only reach equilibrium faster. That's the concept of the catalyst. Before I start further, you know me, Kampi Pongpai, stay there. You probably have seen me walking around, in Amazon or in the cafeteria. Okay. Let's continue. Before I start any further, I think we have to look into the term catalysis a little bit and how cool this is. Because when you look at the greatest prize, I would say, in the world that a lot of people know or give privilege to will be the Nobel Prize, right? And I think how come we have this Nobel Prize thing, everybody knows. But what I want to point out would be during the past over 100 years, there has been more than 10 Nobel Prize awarded to catalysis. Okay, so that means this is quite a significant thing, especially like the last year, 2022, we have this guy, especially this guy, K.B. Chaplet, he got Nobel Prize twice. In real life, there are only a few people who receive Nobel Prize twice. One of them is, I forgot his name, got stuck into my mind. Anyway, anybody knows? Huh? Marie Curie, who else? What's your name? EQ, maybe EQ, Dr. EQ, Professor EQ. Nobel Prize twice, maybe. You may have to ask for his signature now because later on it will be so expensive, to get your hands to. This guy received Nobel Prize twice and he's still living. Okay, the first one he got like 20 years ago. Now K.B. Chaplet from America, he got it from the click chemistry. I think in another class we teach about the click reaction. It means some reaction that's so efficient, like click like that. It works just like that. Because now you have the A side, you have the triple bond. If you want to connect these two units together, you just add his catalyst, and they are joined together. And it has found so many applications in, I would say, materials chemistry, medicinal chemistry, so many things that you can think of. So this guy is probably one of the best scientists ever lived here for click chemistry. Before that, even a year before that, we got asymmetric organocatalysis from Macmillan and List, Germany. So you can see 2 years in a row, right, for Nobel Prize in catalysis for the chemistry. After that, we have to go back 10 years ago. Nikishi Suzuki coupling, I think cross-coupling reaction. You probably have seen or used some of this Heck reaction, Nikishi reaction, Suzuki reaction. Some of you may have heard these names, right? That's 2010 goes went back 5 years earlier. Schwann, Graf, and Schwab. This is for metathesis reaction. Metathesis is a reaction that, let's say, who has some organic background? Anyone? Anyone? Okay, you? Okay. Let's say if you have a double bond. Okay. If you want to do something with a double bond, for example, imagine Neen and TQ, grab your hands together like this. This is like the double bond, right? Okay. And dear E. Okay, that's the double bond. Okay. If I want to change pair, for example, now TQ and dear, will go together, and Neen and E will go together. Something like this. This reaction is very difficult. That's it. Thank you very much. This reaction, now you have to marry her. Sorry. You can't resist, sorry. Sorry. You see, this type of reaction is actually very, very difficult, okay? Because you have to break the double bond, right? And then form a new bond. So this thing is quite difficult. But with his catalyst, Schwab catalyst, Graf catalyst, and this is the guy who worked out a lot in mechanism, it works like very quickly at room temperature. So this reaction with the help of the catalyst. So they got a Nobel Prize, which is really, really cool, these two guys. Knowledge, Nourish, sharpless. You see this guy here? After, this was in 2001, right? You see his face? Now, this is how he looks like. You can see the face, how he changed during the past 20 years. KB sharpless, okay? Lose a lot of hair compared to like, 20 years ago. Yeah, I think KB sharpless. For the, this one for chiral catalyzed oxidation reaction, chiral catalysis basically. And after that, you have to go all the way from 2001, all the way to 1975, a long way, Pre-gold, Cal-in-gold, P-log, I think you probably have heard this term here for organic molecules and reaction. Fischer-Wilkinson, this is another name that is so familiar. Fischer-Wilkinson, it's about sandwich compound. Let me ask, anyone comes from Mahidol University? Anyone? No? No? Okay, Mahidol, what about chemistry? Mahidol? No? What? Chemistry, okay. Probably you are the only one who made ferrocene in the inorganic lab, right? Okay, so this is the guy who did all that work, He has like a cyclopentadiene. It's like a planar ring here, and another cyclopentadiene. A sandwich complex with iron compound in the middle, just like that. And that was like a milestone for modern organometallic chemistry, I would say. So they got Nobel Prize in 1973. Before that, we have Siglanata, I think, for petroleum chemistry. You're from petroleum program? Petrochemical, I'm sorry. Petrochemical industry. So you have seen these two guys probably, like Siglanata catalyst, like polymer. You'll see later on, okay, you'll see later on. And we will cover some of this work a little bit as well. All right, Siglanata is the polymer synthesis. And then we have to go all the way from 1963 to 1918 for Fritz-Haber. Anybody knows what? Have you ever heard of the Haber process? What is it about, Haber process? Some say it's a Haber-Bosch process, but yeah.
Nitrogen fixation, synthetic.
Synthetic nitrogen fixation. There was a time, in the world when you imagine in terms of fertilizer, what is the main elements for fertilizer? Anybody knows? We have 3 elements, necessary elements. We have nitrogen, N, and P. What else? What's the last one? K. Thank you very much. We have NPK, right? The 3 major elements necessary for plants. But phosphorus and potassium is okay. I mean, it's everywhere. But nitrogen is a problem because we may have we may run out of nitrogen, because when you think of the nitrogen, how do you get nitrate or nitrogen into the soil? When you think about it 100 years ago, now you can just go to maybe 7-Eleven, you can get some, maybe not fertilizer, they don't sell fertilizer, right? Okay, anyway, it's very difficult at the time, because how do you get nitrogen? I'm not talking about like 1 gram, 2 grams, we are talking about tons, 100 tons of nitrogen source. It's very, very difficult actually. So this guy came in, he wants to change nitrogen from the air. Nitrogen gas turns into nitrate. So if we can do that, because nitrogen in the air is what, 70-80%, right? So that's a lot of nitrogen source in the world. So he did that, and then he got the Nobel Prize with the iron catalyst, and so he has nitrogen N2 and then hydrogen gas, so he can make ammonia, and then can be changed into nitrate and other things. So that's the guy. But because of his discovery, actually, during that time, it was during the First World War. Actually, if you can notice, he has a major role in chemical warfare at the time, like gas warfare during that time. So that was quite controversial actually, when he got a Nobel Prize for something that should be, beneficial to the world, to the people, right? But the work he has done is actually was used, and he also got involved in the chemical warfare during the First World War, and ended up his wife pledged him to stop working in this area, but he refused, so his wife killed himself, like to protest. It was quite a sad story actually about him. Anyway, that's the ammonia synthesis, okay, from nitrogen. And the first one was oswald process. That's the nitric acid synthesis. Okay, so you can see about 10 Nobel Prize winners, okay, that we can in catalysis. Okay. So if we, as I mentioned earlier, if you want to classify catalysts into something like homogeneous, heterogeneous, these are the very simple way to differentiate between the two. Heterogeneous is insoluble, right? You have 2 phases. Homogeneous, you have 1 phase. So everything is soluble in the media. So the drawback will be it's hard to separate, easy to separate for the catalyst. Homogeneous is normally used low temp and low pressure normally, but for homogeneous it's normally require quite high temperature and pressure. High selectivity for homogeneous, poor selectivity for the heterogeneous in general, okay, in general. And easy to modify for homogeneous, because a lot of time, as you will see later on, if you want to change some ligands on the metal, you can do that very easily and systematically as well, compared to the heterogeneous, in which it's more difficult, to look at this. But as you can see, looks like there are a lot of advantage here, but it's only not used a lot in industry. More than 95% they use heterogeneous catalysts. The reason is, in industry they don't want something fancy, really, something cheap, something that can be done, cheaply in industry scale. And large scale, you don't have to do anything much. You don't even have to know anything much about a compound. Just have some recipe, it works, that's it, they'll use it. That's why during the past 100 years, there has been a lot of development in the catalysis, in heterogeneous catalysts. Okay, here are some examples of top 20 synthetic chemicals in the world, from sulfuric all the way to methanol. And you can see heterogeneous process, heterogeneous. A lot of them use heterogeneous catalysts, but some will use homogeneous, like this one. What else? That's it, probably, not many, like I said, not many processes use homogeneous catalysts. But like I said, we use it when we require some high selectivity. Chiral synthesis for drugs, for example, like drug synthesis, definitely you gotta use homogeneous catalysts. Okay, and here are some examples of other things that you can have a look yourself. So today I want to focus on the olefin polymerization. Okay, the reason I want to focus on this, because olefin polymerization actually use a lot of homogeneous catalysts, and it has been shown to demonstrate the selectivity very well, and you can kind of predict the outcome Okay, so that's why I think this is quite important. It started off during the 1950, 1960. Ziegler and Natta, these two guys, like I said, they got Nobel Prize. This guy studied polyethylene using the titanium 3 for the titanium 4, that's the Natta. And later on, it's kind of a mixed system. So people refer to this simple salt system and the aluminum salt as the Ziegler-Natta catalyst. And I think this is the term that you probably have heard earlier, Ziegler-Natta catalyst. All right, and let's see, what's the benefit then? Olefin, I think you use it a lot. If you look around, it's actually everywhere. Plastic bag, well, bottle is PET, that's a different thing, but you can see there are many things that, we use polyolefin, either polyethylene, polypropylenes. These are the two major components that we use around the world now, mostly for packaging, definitely, and building and construction. Okay, polyethylene, lightweight, and other thing you can take a look at it yourself, but they have quite high TM. It's about 130 degrees Celsius, and different kind of polymers. They have different structure, like linear, okay, long branch, short branch, extensive, like branching, for example. All of them have different property. That's why even a small change in the structure of the polymer can give you different materials. And I remember in Thailand, actually, in Thailand we use a lot of, let me skip quickly. Okay, I'll come back to my point, to that slide, but I just want to finish this. Okay, different structure, right? Branching and so on. And also like different type of structure. Linear, high density polyethylene is all linear polyethylene. If you have some branching like this, we call it linear low density polyethylene. Metallocene, linear low density polyethylene, and so on. It's just different structures that give you different property. The reason I want to mention about this is normally when we run polymerization for double bond, okay, one catalyst that a lot of people may think of is the radical process, right? I mean, you just use a radical initiator, put it in there, the reaction will take place. Okay, like nowadays we probably think of like what is it? ATRP, or atom transfer radical polymerization or something like that. But before that, it's just a simple high pressure free radical process. The company that is still using this technology, this is about 50 years old technology, is PTTGC. I think they still use it, and also like in SCG, they still have this plant. Okay, you have to use quite high pressure and high temperature. Actually, it's about 200 or 300 degrees Celsius. Pressure is about close to several hundreds bar, actually. So when you have a reactor, they must build a thick concrete to cover the whole thing. So if it explodes, then it will be safe inside. And after that, we have like a Ziegler process, metallocene catalyst process. I'll cover that later on. And some of them, they have different structure and then give you different TM, melting temperature, and also like the density of the polymer. You can look at later on. But one thing I want to point out is when we look at polyethylene, it's a long chain, CH2, right? Nothing much, just branching. But when you look at the propylene, okay? When we look at the propylene has, I don't have something to write on, but this is the structure of propylene, okay? This is the propylene. We have double bond, and then we have methyl group. Okay. For the propylene here, if you use the catalyst, then you get polypropylene with one methyl group hanging here. But I think from your chemistry knowledge, you will see that there is also a proton, right? So that means this methyl group can be either, if this chain is on the plane of the board, this methyl group can be either up or behind the board, right? It's either up or down. So the orientation of this methyl group actually influence the property of the polymer, and you can actually control it with the catalyst, with the right catalyst. So I will cover a lot with, from that one. For example, if the methyl group is all up, you see? Okay, before I move on, I think for the chemistry major, they know thick line means methyl is hanging up, right? If you have a dashed line like this, it means methyl is behind the bond. Okay, that's what it means. So this means methyl group is higher, up. Okay, so we call it isotactic polymer, isotactic polypropylene. And another polymer that methyl is up, and then the next one is down, up, down, like this. Alternately, we call it syneotactic polymer. Okay, syneotactic polypropylene. Or sometimes we can have up, down, up, down. Okay, this is called heterotactic. And sometimes you can also have something like methyl up. The next one, this symbol means either way, random basically. Up, the next one, random. Up, random, and so on. Hemid means, this is, okay, up is isotactic, right? Hemid means semi basically, like half isotactic. You can put it that way. So they call it hemi-isotactic. Or you can have like isotactic block and then atactic block, or completely random, atactic polymer. So there are many, structures that you can think of, but the question will be, how do we control it? And how can we design the catalyst to make this kind of polymers? Because all of them have different structure, different properties. Okay, and all of them has found applications in industry already. So today, at the end of the class, today here, when you look at the catalyst structure, you will be able to at least make some guess. Okay, what would be the final product if I use this catalyst that has this structure? By just looking at it, analyze, and then use some point group. I know some of you have still remember point group. C2V, CS, C4, D4H. Does anybody ring a bell? Anyone? Okay, this senior year, so they probably have seen this because they took my class. Chemists, have you ever heard of like CS symmetry? Anything like that? For Chem N, I don't think they teach that, right? Okay, don't worry about that. We don't use that a lot today, but I will give you some guideline. That's all. So before I continue, this is the timeline for polyolefin synthesis. Okay, we start off during the mid 1930, high pressure radical polymerization at the time, and the next phase we start to have cyclaneta comes in. And from this process, they develop into the gas phase process during the 1970, 1990. And after that, we start to have homogeneous single site catalyst or metallocene catalyst, starts to jump in. So today, we'll focus on this one. And later development will concentrate on copolymerization with polar monomer, for example, that can, even develop the property even further. So we'll focus on this one. Just properties of polyolefin using the metallocene catalyst, controllable molecular structure, and new kinds of polymer can be synthesized. Here are some examples. You can mix between ethylene, propene, even diene there, or some alpha olefin like 1-butene, 1-hexene, for example, norbornene, and many other things can be done using the metallocene catalyst. That's why today I'll focus more on the metallocene catalyst. All right. But before we start with metallocene, I want to explain a little bit. Some of you who doesn't know what metallocene is. Metallocene refers to the bicyclopentadiene. Actually, it is this. The structure looks like this. We have carbon atom here, right? C5, and then normally the R group is hydrogen. Okay, so we have hydrogen here. So it is C5H5. That is cyclopentadiene. Okay, and if you count the number of electrons in this, you can count it to 6 electrons. That means this is like a aromatic pi system, 6 electrons. So it's stable. That's what it means. Okay, when you count electrons in the pi system, and you come up with 6 electrons, 6, 10, 14, and so on. That means it's stable. So that's why a lot of people go into this field and make this complex. it can wrap around two metals to make sandwich complex like this, or bend structure like that, or many other variation. Okay, that's what it means, like the term metallocene with the cyclopentadiene framework. All right, okay, let's take a look at the history of the catalyst in this field first. So we start off actually with someone did some work with CP2. Okay, I forgot to mention. C5, H5, we call it cyclopentadiene, right? The name is called CP. Okay, it is a negative one, so we have like CP minus. That's what it means. Okay, so it is a negative one ligand here. So if we connect the CP into titanium, where is titanium in the periodic table? Anybody knows? What group number? Some of you took my class last week and then asked, please memorize the first 30 elements. Where is titanium? What group number? Okay, we start from periodic table, right? This is the periodic table. We will have hydrogen, helium, lithium, beryllium, boron, and so on, right? Until you hit to potassium, magnesium. That is 1920. Okay. The next one will be scandium and titanium, right? So potassium, magnesium, scandium, titanium. Titanium will be group 4. Right? So that means it can have like 4 plus charge. That's the valence electron. Group 4, 4 plus. Okay. So 4 plus, that means chloride, the charge is -1, right? Like sodium chloride. Sodium chloride. Sodium +1, chloride is -1. So chloride is -1 here. We have 2 of them, so this is 2 minus. CP is -1, right? I told you earlier. So we have 2 CP, so that's -2. -2, -2 plus 4. So you can see that the charge is balanced for this catalyst. So this guy polymerized, did the polymerization with triethyl aluminum, TEA. Okay, the catalyst, okay, you can polymerize it, but the reactivity is not that good compared to the cyclaneta catalyst. Not good at all. So not a significant development. But 20 years later, from 1957 to 1975, Breslow actually did a mistake. Okay, he did this reaction, CP2 titanium chloride, and then he reacted with dimethyl aluminum chloride there, and then unintentionally introduced moisture because he did not seal the system very well. Okay, moisture accidentally got into the reaction, but somehow the reactivity goes really high at the time. So what happens, when you found, oh, I did some mistake, what would you do? Throw it away or? But this guy, no, he didn't. The graduate students didn't throw it away. Report to his advisor and then discuss what's going on, and then found out that the water got leaked into the system, and somehow this water react with something here, and then you get some super active catalyst. And then later on, a few years later, next year, Kaminsky came out and then found out that actually if you use trimethyl aluminum mixed with water first, 1:1, you get what is called methyl aluminoxane, or MAO. And this is actually the one of the most active activator in the world. And he found out, okay, if you pre-make this and mix with whatever you want, the reactivity will go up really high. So just something to remind everyone, if you screw up, okay, in the lab, don't try to, not cover up, but gather yourself, bring yourself back in and try to understand what you did wrong, and you may get some interesting result afterward. Okay, we had a similar situation in Vistech in my group actually, when one of my graduate students, she already graduated and now work in IRPC. We did some polymerization of epoxy and cyclic anhydride. You get alternate polymer. That is normally what people have done. Okay, we get monomer A and monomer B, right? And the result will be A, B, A, B. It's alternate polymer. everyone gets this kind of polymer. But then one day, Pilupo came to me and then something weird with the reaction, because when she polymerized with the tin catalyst, somehow the NMR doesn't look like what has been published in the literature. You see some peak that correspond to what published in the literature, what has been reported, but we found more peaks in there. It's tiny, it's about 20%, not much, but she doesn't know what it is at the time. We didn't know what that is at the time. What would you do? I mean, if you are a graduate student, maybe, well, let's try again, or maybe we did not purify good enough, right? And she repeated, and then it's still there, it's still there, but we don't know what that is, because no one has reported this peak before. So after a while, when we look at this, try to characterize and found out that that peak is real. Actually, it is attached to the polymer chain, and we found out it's not A, B, A, B, A, B like that, but it's actually A, B, B, A, B, B. You have one B unit, additional units there, and that changed a lot of properties of the polymer actually. And afterward, E did some more work with the tin catalyst. Now we can control these B units and explore more things, more fun thing about that. So that's just one example that, sometimes you found something unintentional, in the lab. Please try to understand it. You may get something really, really useful. Similar to this guy, okay? Now MAO is a standard activator in industry actually. After that, he changed from titanium to zirconium, right? And then he found out the zirconium is actually more active than titanium, so activity goes up a lot, even higher than signal netta catalyst. So now the industry are more got interested now, because originally the reactivity is really low. Now it got so high. Okay, that's a brief history of this thing. But a lot of them, if you polymerize polypropylene, you get atactic. Okay. If you are in the polymer area, like polymer field, if you want to make some materials, the materials, to get a strong materials, the compound or the polymer must have a certain degree of crystallinity. Okay, must have a certain degree of crystallinity. It could be 50%, 60% whatsoever, but it must contain some crystallinity, because that is like the strength of the polymer. Okay, like polystyrene, for example. I think you use foam, like a polystyrene foam, right? You put food in there. Nowadays, I don't see many people use the white foam anymore. Or when you go to 7-Eleven or some shop that sell like the cup, if you when you go like a cup for party, not the paper cup, but like a plastic cup. I think there are a few kinds of plastic cup that you can notice. One is a clear, kind of very clear, but rigid. I don't know if you have noticed. You grab it, it looks really rigid, really strong. This is polystyrene. TG is about 100, so it's really rigid cup. But another type of cup is kind of softer, but opaque, kun. Right? I think you have seen that. It's kun. Opaque cup, softer. That is polypropylene. Okay. Sometimes you see kind of clearer, still soft. That can be either polyethylene or maybe they use PET, like this one as well. If you look at the bottom, you see what the design there. It said there. What I want to mention is this comes down to crystallinity. Okay. If you have good crystallinity, then the polymer is strong. But if you have atactic polymer, crystallinity means you must have a certain repeating unit, right? So it repeats and then forms a crystal. Just like when you want to grow crystal, basically, it has to be like a repeatable, in the lattice. But when you get atactic polymer, up, down, down, up, you see, it's random. So you don't get a strong material at all. So that's the drawback, okay, at that time, because all of them, even though this is highly active, but you get atactic polypropylene. But then later on, people found out a few years later, you can make isotactic polymer from this catalyst, okay, and you can even make syneotactic polypropylene. So after that, people understand how this thing works. That's why I mentioned when we use metallocene-based catalyst, you can produce a lot of polymers afterward. 1980s, Stephen report what we call constrained geometric catalyst, and Dow Chemical actually patent this and give it a name Insight technology. It means it is the cyclopentadiene like this. You have CP on top, okay, and then you have the amide group like this. Link them together. Imagine like this. This is this is cyclopentadiene, right? Like this one. If you want to make just CP2 titanium dichloride, it looks like this. This is like 2CP, and then if you want to make titanium dichloride, structure will be like this with 2 chloride hanging, okay, just like that. But if you want to make the compound more active, you must increase the space around the metal, right? So one way to do that is they link the 2CP together with something, carbon, silicon, whatsoever. You have to link them. If you link them together, it's gonna open up more like that, so you get higher activity. But this guy, Dow Chemical, rather than tie this up, they tie the bottom part with the amido, which is the amido group here is smaller than the CP group. So this part is wide open. You can put so many things in here. Like the monomer can come in and then do the reactivity very quickly. So they patented this, and this is, I would say, among the fastest catalysts now for the metallocene base. Not the fastest in the world, okay, but very, very good one nowadays. So before I move on, I want to explain a little bit about the term single site catalyst, because if you understand this, you can use this concept actually to do catalysis with homogeneous catalyst. The concept is very simple. Actually, single site catalyst, that means you have just one site, right, to do the polymerization, to do whatever you want. But when you compare to something like heterogeneous catalyst, imagine like, okay, so that the video can see. If this is the heterogeneous catalyst, this is the catalyst. Imagine this is the monomer comes in, okay? The monomer can come in and interact with this space, right? That's one reactivity, one rate here, one propagation rate. If it attacks at this corner, you see that it's totally different from this side, right? So you may get a different kinetic, right? A different rate. Or the bottom one, or how about the one on top, or something in the angle like this one. So you can see that heterogeneous catalyst can produce multi-phase and then multiple sites for the reactivity, for the reaction to occur. So it's more difficult to control, really, because when you have heterogeneous, you can't force it to have only one phase. It's a mixture of several things. I mean, in some work you can control, but a lot of them you cannot. So the single site catalyst actually helps to improve that, because the structure looks like this. You have the ligand, you have the metal, and this is the initiating group. You have only one site, which is this one metal, to do the reactivity and everything. So that's why if you can control the ligand here, then you can control reactivity, everything. The design will be very simple, like a metal ligand and initiating group, right? The A is the monomer. Monomer come in, insert into between M and X, give you something like this. The next monomer comes in, inserted, react at the M position, and then insert between M and A, like this one. The next one comes in, it will be inserted between this unit, and so on. So that's why all reaction occurs at the metal center, right? So if you can control the ligand, then you can control the metal, and then you can control selectivity of the monomer as well. That's the concept of single site catalysis. You can do a lot of things. You can grow crystal, get crystal structure. You can change the R group, increase steric hindrance, increase electron withdrawing group. You can do systematic modification. And single site, so one site it's easy for mechanistic study. Right? You can do like kinetic run, get some useful information, and you have a lot of control. That's the good thing about this. So before I continue, the rest we will start with olefin polymerization. We'll have a quick break. Okay, just this time it's a good place to stop. Any questions before we have like a 10 minutes break? No? Okay, then let's have 10 minutes break. Okay, so you can stretch, relax a little bit. If you have any questions, feel free to come down and discuss. ตามทันไหมแทบหลับเลย ครับ